Alrighty folks, today we're looking at composite inverse trigonometry, how we evaluate these statements. Now, I know you might be thinking a bit of, composite functions are something we talked about back in marking period 1. They took the form of f of g of x, wherein we would first solve for our innermost function, then take the output and rewrite that as our value. So if g of x equaled y, we could rewrite our whole statement as f of y. As for inverse functions, these are things we've been using for a while now. An inverse function is any function that undoes another function. In the same way that addition and subtraction undo each other, multiplication and division undo each other, squares and square roots undo each other, and most recently, you've seen normal and inverse trigonometric expressions will undo each other. So essentially, we're building composite inverse statements and solving them. A composite inverse statement is created when we evaluate with more than one trig function present. These take the form of usually an inverse function paired with a normal function. The order doesn't necessarily matter. For instance, example problem, we have the cotangent of the cosine inverse of 0. We would first solve for the cosine inverse of 0. That is, say we would find the angle theta that occurs at cosine inverse of 0. Whatever that is, plug that back in, and then do the cotangent of that angle. Sometimes, though, we'll be lucky enough that our outside and our inside are inverses of each other. In this case, the inverse sine of the sine of 5 pi over 4, our inverse sine and our normal sine cancel each other out, leaving us only with 5 pi over 4. So let's take a look at some example problems. First, we have the cosine of the inverse sine of square root of 2 over 2. If we take a look at our unit circle or our trig table, the inverse sine of square root of 2 over 2, that is to say what angle is produced by the inverse sine of square root of 2 over 2, that's going to occur at 45 degrees as well as 135. So theta could equal 45 degrees, or it could equal 135 degrees. So this allows us to then rewrite our statement as the cosine of 45 or the cosine of 135. Cosine of 45 gives us our square root of 2 over 2. Cosine of 135 gives us negative square root of 2 over 2, where the cosine of 45 exists in quadrant 1, and the cosine of 135 exists in quadrant 2. Now, for the actual problems, I will tell you what quadrant I want you to focus in, and that's what we'll work off of. So if I said, give me the quadrant 1 answer, you would then give me the square root of 2 over 2. Problem 2. The inverse tangent of the tangent of 5 pi over 6. Well, inverse tangent and tangent cancel each other out, leaving us only with our 5 pi over 6. The tangent of the inverse cosine of the negative square root of 3 over 2. So first things first, we solve our innermost bit. What angle theta is equal to the inverse cosine of negative square root of 3 over 2? Consult our unit circle. We find this occurs at two locations. This occurs at theta equals 150, as well as theta equals 210. I swear that's 0, folks. So I can now rewrite this as the tangent of 150 is equal to something, or the tangent of 210 is equal to something. The tangent of 150 gives us negative square root of 3 over 3. The tangent of 210, positive square root of 3 over 3. 150, that occurs in quadrant 2. 210, that occurs in quadrant 3. All right, so that's that for those example problems that occur on the unit circle. But what if we want to do complex inverses with our non-trig values, like trig for any angle? Well, if it's not on the unit circle, we're going to use triangles. Exact same way as we did for our trig for any unit. We'll build a triangle, build a reference triangle, take a look at our angle, and use that angle to solve for everything else. So for example, we want to find the exact value of the following. The sine of the tangent inverse of 5 over 12. Now for this, I'm going to assume quadrant 1. Making that assumption because my tangent value here, tangent is my opposite over my adjacent, 5 over 12, they're both positive, so this could occur in quadrant 1 or quadrant 3. Because I want to keep this simple for y'all for the example problem, we're going to assume quadrant 1. So we're going to draw our triangle in terms of quadrant 1. And what do I mean by simple, folks? Well, if we don't have to draw in negative signs, we don't have to clutter up our page with negative signs. So the angle in question we're looking at is right there. We know that the side opposite that is 5, and the side adjacent to that is 12, because from our problem we know that 5 is our opposite and 12 is our adjacent, also known as the 5 being our y value and the 12 being our x value. So now we can either remember that 5 and 12 are part of a Pythagorean triple, with the third number being 13, or if we forgot that, we can use our Pythagorean theorem such that a squared plus b squared equals c squared, which means then that 5 squared plus 12 squared equals c squared. 5 squared is 25, 12 squared is 144. These add up to give me 169. So 169 is equal to c squared. If I take the square root of both sides, 13 is equal to my c value. Now, what's that matter? So what? Well, since we found our missing side, again, we're looking at this angle here. We want to find the sine value of that angle. Sine is my opposite over my hypotenuse. So the opposite side from that angle is 5, and my hypotenuse is 13. So the sine of the inverse tangent of 5 over 12 is equal to 5 over 13. Again, folks, first thing we did, we identified what quadrant it might be in, drew our triangle for it, and plugged in our corresponding values. This next one, the cosine of the arcsine of negative 8 over 17. Now, you may recall, and if you don't, that's fine, that arcsine is just another way to write inverse sine. Depending on the country you're in, or the country that your textbook was published in, or how old your textbook might be, or problem set might be, arc might be used in place of inverse. So we could rewrite this essentially as to find the cosine of the sine inverse of negative 8 over 17. So we're going to start off with our innermost bit, the inverse sine of negative 8 over 17. So for what angle theta will we have a sine inverse of negative 8 over 17? Well, sine is our opposite of our hypotenuse. So we have an opposite side, a y value that's negative, hypotenuse that's positive. That's going to occur in either quadrant 3 or quadrant 4. For simplicity's sake, I'm going to go with quadrant 4, just so we can cut down on the amount of negatives we use. So build our reference triangle. In quadrant 4, I'm looking at this angle here, and I know that my opposite side is 8, my hypotenuse is 17. This is also a Pythagorean triple, with the last side being 15. But in case we don't remember how to do that, we could use our Pythagorean theorem, such that a squared plus 8 squared equals 17 squared. A squared plus 64 is equal to 289. Subtract 64 from both sides. We get a squared is equal to 225. If we take the square root then of both sides, we get a is equal to 15. So we want to find what the cosine is of this angle. The cosine is my adjacent side of 15 over my hypotenuse of 17. So 15 over 17 is my final answer. And that, folks, is how we solve these sorts of problems. If you have any questions, please let me know. Otherwise, folks, good luck on the assignment and any subsequent items therein.